Okay, so welcome everyone to another episode of TCS Plus. Today with Shayan Oveis Gharan. Before we start, I should as always, thank my co-organizers. It's Clément Canon, Thomas Vidic, Gautam Kamat, Ilya Rosenstein, and India De. So again, today's talk is by Shayan, and before I introduce Shayan, let me quickly go around the table as we usually do here. There's Anidia is here. Hi, Anidia. And there is Ben Lee Volk from Caltech, the group from Caltech. We see a few hands. Clément Canon, the group from Stanford. We have Inbal Talgam Cohen from the Technion. Hi, Inbal. We have Sam McGuire from UCSD. Hi, guys. Shengeng Wang from the University of Michigan. And one more group. We have Shuai Xiao from University of Wisconsin-Madison. Hello, everyone. Okay. So back to me. So yeah, just briefly introduce Shayan and we can start with the talk. So Shayan is currently an assistant professor in the University of Washington. He graduated from Sharif University in 2008 and then decided to explore the West Coast. He started in Stanford doing his PhD with Amin Sabarid, and he was a postdoc at UC Berkeley and then joined the University of Washington. He won many awards and honors, Sloan Fellowship just now, 2019, NSF Career in 2016, and 2 Best Paper Awards in Fox 2011 and Soda 2010. And of course, the biggest honor is that this is his second TCS Plus talk. Great, so I think we're ready to start. So welcome, Shayan.
Okay. All right. Hello, everyone. I should thank a lot the organizer for inviting me. I think this is a wonderful thing, the TCS Plus. I always enjoy watching the talks. So this is a joint work with my wonderful co-authors. Quickly, Leo is my student at University of Washington. Nima Nari is like my close collaborator. He's currently a researcher at Stanford, and Cynthia Winzan from North Carolina State University. So basically, this talk is about a number of concepts, and as I go through the talk, I will try to introduce these different concepts and tell you how these are related to each other and how we can use them to design algorithms. So presumably there would be less proofs, more of connecting different things. So let me start by telling you about matroids, and then I'll tell you the problem that you're interested in. Sorry. Oops, okay. So hopefully many of you are familiar with matroids. Just let me go over.
Shayan, sorry, the slides aren't getting displayed anymore.
Oh. What happened? Oh, what happened?
Let's press the red button. Yeah, we lost the slides.
Maybe, okay, maybe I can stop the screen.
Yeah, maybe we start.
Yeah, let's
okay, it's good now.
You're back.
Wait. Do you see now?
Well, it's okay. Okay, it's back now, but it went again back. Okay, it's back now. It's fine. Okay, let's not.
Okay, good. So let me first remind you of what is a matroid. So matroid is a family of subsets. So basically, I always assume you have a ground set of elements, let's say 1 over n, and you have a family of subsets of this ground set called independent sets. They have 2 fundamental sort of properties, the downward closeness and the exchange property. Downward close says that a subset of an independent set is also independent, and exchange property says if you have an independent set bigger than another, you can add an element from the bigger one to the smaller one to get another independent set. They're basically, I think they first started back in like 70 or 80 years ago to study, to sort of generalize the notion of linearly independent set of vectors in a sort of abstract sense. And you can see these properties are trivially whole if you have like vectors and you're talking about a family of vectors to be independent if they're linearly independent. Now you can define rank and bases similar to the way you define it for linear spaces. A base is like a maximal independent set, and you can see all maximal independent sets have the same size. The rank of the matroid is the size of the maximal independent set or size of the bases. And in the talk, I'm going to assume that the matroids I'm going to work with all have rank R. And there are many examples. So I already talked about linear matroid. Another famous example is a graphic matroid, where you have like a graph and a set of edges of the graph is a independent set if it is acyclic, if it doesn't have any cycle. Okay, so this is about matroids. Okay, now, like one simple nice property of matroid is that they have a lot of closure properties. The first one is called the deletion, which is similar to the deletion of an edge in a graph. If you have a graph, you delete an edge, you get another matroid. In this case, you get another graphic matroid, but this is true for every matroid. Another one is the contraction, which is again similar to what we do in graphs. So if you have a graph, you contract an edge, you get another graphic matroid, and this works in general for any matroid. There's another closure operation is the truncation operation, where you sort of choose an integer k and you remove all independent sets of size greater than k. So you truncate all your independent sets to those that have at most k elements, and your bases will have at most k elements as well. This also preserves matroids. Now, okay, so now we know a little bit about them. Let me tell you some fundamental questions. The first question you can ask is that, how is optimization? Can we do optimization over matroids? And this is a question which we know very well. First of all, in a sense, matroids are exactly class of objects where the sort of the analog of Kruskal's algorithm for minimum spanning tree works, and it gives you the minimum or maximum base. Edmonds studied the convex hull of the indicator vector of basis of a matroid, and he basically studied so-called matroid-based polytope, which is exactly the convex hull of the indicator vector of these bases. So here I show you an example. Like if you look at the matroid in the left, here are the bases, and this is exactly the polytope, the convex hull of the indicator vector of the bases. The nice property about this polytope is that the edges of the polytope between two bases are exactly of this form, like indicator of I minus indicator of j for two elements I and j. And in fact, this exactly characterizes a matroid. So matroids are exactly objects that, if you look at the polytope, the convex hull of the bases, you get this property. Or in other words, if you have a polytope such that all edges are of this form, the vertices of this polytope correspond to bases of a matroid. Okay, so they have this nice geometry which can be characterized this way. We can do optimization over this polytope. You can optimize any convex function. We have separation oracle. We know it very well. But the question I want to ask is about counting. So the thing is, whenever we can do optimization, you can ask, can we do counting? If we cannot do optimization, we cannot do counting. That's easy to prove. But typically, if optimization is in P, you expect to be able to do some sort of counting. So this was a question asked by Mihail and Vazirani 30 years ago, that given a matroid, can we approximately count the number of bases of that matroid? Okay, and again, here by given, I mean that so you have to be clear here. I mean that there is an oracle that you can ask if a given set is independent, and the oracle says yes or no. Okay, so given access to such an oracle, can we count number of bases? And it is known that it's basically sharply hard to count them exactly, so we're interested to count approximately. Okay, so that's the problem I want to talk about. Before talking about that, I want to tell you why this is important, and tell you that there is another way also to think about it. So let me first tell you that, and then tell you why it is important. So there is this known fact in counting field, which is that whenever you can count, you can sample, and vice versa. If you can sample, you can also count. So let me tell you this, because this would be our main thing. So instead of counting number of bases of a matroid, I'm going to sample bases of a matroid, and that would be in some sense it would be easier, because there are we can use randomness to sample bases. So how can you go from sampling to counting? So let's say you have a oracle that generates random bases, like uniform random bases of a matroid. I want to use that oracle to count number of bases. So suppose mu is a uniform distribution over all bases of my matroid. I can define let's say this probability of I is the marginal probability of an element. What I can do is that I can just call this oracle repeatedly and see how many times, say, the first element or the ith element is sampled, and just by using laws of large numbers, if I sample like polynomial many, I can get a good approximation, like good multiplicative approximation of the marginal probability of an element. Now, once I have that, I can do the counting, because fix an arbitrary base, let's say 1 to r. 1 over the number of bases is exactly mu of b, because I looked at the uniform distribution. And now, just using the base rule, the probability of b is just the probability of 1 times probability of 2 condition on 1, 3 condition on 1 and 2, and so on. So I just need to estimate each of these probabilities. But the thing is, I already told you that when you contract an element, when you condition an element, it is a contraction, and I already told you that contraction is a matroid. So if you can count bases of a matroid, you can also count bases of the contracted matroid, and you can just estimate all of these marginals, and the rest is just simple. If you have like 1 plus epsilon over r approximation of each term here, you get the 1 plus epsilon approximation of the product. Any questions here?
Yeah, I've got just a small question about the second line. So you can only compute a multiplicative approximation of things that have like a non-incredibly small probability, right?
Yes. Okay. Good. Yeah. So there's I'm hiding that over the rug. Yeah, you're right. So if this marginal probability is very small, then this is not enough to do the Monte Carlo simulation. So what you can do is, in fact, not choose a. You can choose a marginal. There is a marginal which is big enough, say at least 1 over r, 1 over n. And you can estimate the marginal probability of that element. So basically, you're not going to fix a one base. You're just going to keep condition on elements which have sufficiently big marginals, and then take the product. Okay, but that's a minor thing to figure out. All right. So having that said, let me tell you, like, for one slide, why this is interesting. I'll tell you more applications in a few minutes, but here is one interesting application. Let's say that you have jobs and machines. So these are like some jobs. I want to run them on machines, and an edge here means that this machine can run this job. Now, I'm in the setting that each machine will fail with some probability, and let's say these probabilities are given to me. At the end of the day, I want to match the jobs to the machine. So my question is that what is the probability that I can match the jobs to the machines? So for example, here you can see that, like, with this probability, the bottom 2 machines fail and there is no matching. But with 1/15th probability, maybe only the middle one fails and still there is a match. Okay, so there are exponentially many possibilities here, and I want to basically estimate how reliable is my system by estimating the probability that I can do the job. Okay, so this is a special case of a problem I'm thinking about, where the matroid is so-called a transversal matroid. So if you can count bases of a matroid, you can solve these type of questions and get 1 plus epsilon approximation. Okay, so there are more applications, but let me, in the interest of time, not talk about that. There are a lot of previous works on this problem. Basically, there are a lot of special classes. There is this class called balanced matroids. I'm going to tell you about it in a few minutes. But that's basically what we know. So essentially, it's like we know for graphic matroids, the bases are exactly spanning trees. So we know how to count the spanning trees. And there is this notion of balanced matroids, which generalizes that. So that was pretty much what we knew before our work. There are other many other results about like weighted versions of these a weighted distribution over basis of a matroid, where it corresponds to object called determinantal point processes. There are nice results about deterministic algorithms, but let me again, in the interest of time, not go over them. So let me tell you our main result. So I told you that all we need to do is to do the sampling, and now once you want to do the sampling, you basically can just run a Markov chain. So the main result is that there is a Markov chain which where its stationary distribution is uniform over all the bases, and the Markov chain actually mixes rapidly. I'm going to tell you what this means, but basically there's a Markov chain. You can run the Markov chain, and it will give you a uniform or almost uniform base of a matroid. And all you need to run this Markov chain is just an independent set oracle. Okay, so that's the main result. Is there any question? Okay, so if not, let me tell you like one more slide about like immediate consequences of this theorem. One is that I already told you that matroids are closed under truncation. Therefore, not only we can count bases, we can count independent sets of size k, just simply by truncating the matroids to independent sets of size k, and then look at the bases, count the bases of the truncated matroid. So in particular, this says that we can count forests in a graph. This was something we didn't know before our work, how to count forests. We can get 1 plus epsilon approximation for counting forests in a graph. Another thing is that I told you about this reliability polynomial. So this, we can also estimate this reliability function or reliability probability for any matroid. And to do that, we need to basically count independent sets of a dual matroid. Okay, I'm not going to tell you what that is, but that's basically, there's another matroid called dual matroid. By counting independent sets there, you can compute reliability. Let me tell you this third application, which is important, and I will get back to it in the talk. So there is this graph called the basis exchange graph of a matroid. So what is that graph? It's basically a graph where you have a vertex for every base, and you have an edge between two bases if their symmetric difference is 1. Okay, so let me show you one example. So let's say here you have a partition matroid. So what's a partition matroid? It's where you have, let's say, n buckets. So here I have 3 buckets, and I can choose one element, at most one element from each bucket. Okay, so I can choose the red or the blue element from each bucket. So there are, here you can see there are 8 bases. Now I've shown you all of the bases in the right, and as you see, there is an edge between each 2 bases if they differ in exactly one element. So in this particular case, if you have a partition matroid like that, the basis exchange graph is exactly a hypercube. Okay. This graph is, if you remember the convex hull of the indicator vector of the bases I talked about at the beginning, this graph is exactly the graph of the polytope, the graph of the convex hull of the indicator vectors of the bases. Okay. So the thing is that it's a consequence of our result that this graph, the basis exchange graph, has expansion 1. Okay. You don't need to know what the definition of expansion is, but basically says that for every set, there are a large number of edges leaving that set. Okay, so this graph has large expansion, and just this fact, in fact, so this was a conjecture of Mihail and Vazirani that this basis exchange graph has expansion 1. The conjecture is tight for the hypercube. So hypercube has expansion exactly 1, and you get the 1 if you look at the dimension cut of the hypercube. So Mihail and Vazirani had conjectured that this is true for every matroid. And in fact, we proved that this is true for every matroid. And just this fact is enough to be able to generate a random base of a matroid, because now you have a graph over all bases. So you can just run the Markov chain on this graph. That's from each node go to a uniformly random neighbor. And just the fact that the expansion is at least 1 is enough to say that the Markov chain is going to give you a uniformly random base. Okay, although the Markov chain I'm gonna study is not exactly this Markov chain that goes like on this to uniformly random base. It's slightly different, but it's basically a reweighting of this Markov chain. So it's like I'm still moving on this graph, but with a slightly different weights. Okay, but it's good to keep in mind that hypercube is a tight example for the theorem that I'm going to talk about.
Can you take it? How is the graph defined? And what is the what are you starting with?
You start with a base. You connect two bases if they differ in exactly one element.
Base of what? It's an arbitrary matroid. What's the initial?
Arbitrary matroid. Yes.
Okay.
Yeah, that's exactly the graph.
And the buckets are they?
Sorry.
What are the buckets generally?
Oh, here the buckets each have two elements. You can have n buckets, and again, each have two elements, and you want to choose at most one from each bucket. In a base, you would choose exactly one from each bucket because it's a maximal independent set. And the basis exchange graph is exactly a hypercube, like in n dimension if you have n buckets.
An expansion is not normalized. So when you say
yeah, this is not the conductance. If you know, this is exactly the expansion. So it's exactly the number of edges over the number of vertices.
Okay.
Yes. So in fact, the proof actually gives you a new method to prove that the expansion of the hypercube is 1. Okay, good. So let me now show you the sort of the path. So there's going to be like 4 concepts I'm going to talk about. The first one is log-concave polynomials, then random walks, simplicial complexes, and local spectral expanders. So I'm going to spend some time on each of them and tell you the story, and hopefully we'll connect them at the end of the talk. So let's start with log-concave polynomials. But before that, I want to tell you let's tell you 1 minute about the previous work. So previously, there are a lot of nice results in this area of Markov chain, using Markov chain to do the counting. The idea is that you can use so-called canonical paths to study expansion of graphs. Okay, so the idea is simple to say. So let's say you have a hypercube. You want to bound its expansion. What can you do? Here is one way to do it. You can construct paths between all pairs of vertices of the hypercube, such that for every edge of the graph, the number of paths that go through this edge is small. There is no edge which gets a lot of the congestion relative to the other edges. So you want to sort of choose these paths such that they sort of propagate almost equally over all edges of the graph. How can you do it for this hypercube? It's easy to see. You basically, let's say you give me 2 vertices of the hypercube here, like the red and the blue, the all red and the all blue. You first choose a random ordering of the bits, and then you correct them one by one. Or in other words, you first say, look at these 3 possibilities, these 3 edges, which gets me closer to my destination. I choose one of them uniformly at random. Then I look at these 2 edges, which again gets me closer to my destination. I choose one of them uniformly at random, and now there's only one possibility. So I go there, and that's one path. But this gives me a distribution of paths, and you can see that this if you use such a policy, each edge will have the same congestion by symmetry, and then therefore you can use this to bound the expansion of the hypercube. Now you can try to use this machinery not just for the hypercube but for any matroid, and it turns out that this machinery works when you have the following fact, that if you look at bases of your matroid that have the element I versus those that do not have element I. Here I'm looking at basically bases that have the let's say element 1 in red, and those that do not have element 1 in red. So here they happen to have element 1 in blue. I want to have a fractional perfect matching between the left to the right. Okay, so if this is the case, if for every element I, bases that have I and bases that do not have I have like a fractional perfect matching, then you can basically extend this argument. So this was the observation of 2 works, Feder-Mihail and Mihail-Sudan, which basically say the following. They say that if your matroid has a negative correlation property, then you can prove that these fractional matchings exist, and then you can use that to bound the expansion of the basis exchange graph. So first of all, what is a negative correlation? It's basically what you expect. You look at the uniform distribution over the bases of the matroid. You say it's negatively correlated. If when I condition on J, the probability of I only goes down. Like by knowing that J is in, I could only be less probable. Okay, so that's called negative correlation. And a balanced matroid is a matroid where M and all of the minors are negatively correlated. So it's known that random spanning trees have these properties, or partition matroids have these properties. And basically what Feder-Mihail and Mihail-Sudan show that is that if you have balanced matroid, you can use it, if your matroid is balanced, you can use it to prove that these fractional matchings exist between sorry. That these fractional matchings exist, and then once the fractional matchings exist, you can use it to generate these paths with a small conditioner that would give you the expansion of the basis exchange walk is small. Okay. Now the question is that are all matroids negatively correlated? This was a question asked by Seymour and Welsh, like back in '75, but it turns out that the answer is false. So in fact, most matroids are not negatively correlated. You can easily run a simulation to find a matroid which is not negatively correlated. Okay, so what do we do instead? What tool do we use instead? The tool that we use is so-called the strong log-concave polynomial. So let me tell you what that is. So we say a polynomial G is log-concave over non-negative reals if log of G is a concave function. Or in other words, if the Hessian of a log of G is negative semi-definite over all x which are positive. We say sorry.
Yeah, question. Yeah. What are you trying to prove now? Maybe just before we go into the technical proof.
So this is the main tool that. Oh, there was a. So yeah, I'm not. So the thing is previously the main sort of way to study matroids was negative correlation, but that doesn't work. So
are you trying to prove that the graph is expanding?
Yes, that's one way to see it. Or sorry, what happened? Google Hangout? No. I want to eventually prove that the graph is expanding, yes, but or study a Markov chain. So I'll tell you that in a second. But first, I want to tell you what I want to use instead of negative correlation. So negative correlation doesn't work. So you cannot use this. You cannot use this sort of canonical path method, which was used previously. So we want to use. We have a new tool, and I'm going to tell you how to use this tool. Okay.
Okay.
So we say a polynomial is strongly log-concave if all partial derivatives of the polynomial are log-concave. Okay. Now, okay. Here is the theorem from our previous work that we showed that the generating polynomial of any matroid is strongly log-concave. So what's a generating polynomial? You simply sum over all of the bases. You look at the product of zi for I in the base. Okay, so this is a fact. This is proved in previous work. Actually, Nima talked here maybe a year ago, and I think he also covered this. So you can take a look at that talk about the proof of this. I'm not going to spend time about the proof of this. I'm going to give you some intuitions. So we proved this. We used this originally to study deterministic algorithms for counting bases, but now we want to use it to design Markov chains. So this fact, you can see, is a generalization of the case of graphic matroids. For graphic matroids, the analogous fact is that determinant of sum of PSD matrices is a log-concave function. And this is a well-known fact. This fact is a generalization, and it works for all matroids. The original proof of this uses so-called Hodge theory, but now we have simpler proofs. Let me not tell you about the proof of this. I'll tell you about how to use it. Okay. Good. Okay, so let me first tell you one thing, give you a little bit of intuition. Let me tell you, I told you that if a function is log-concave, then Hessian of the log is negative semi-definite. Okay, let me tell you what log-concavity says about the Hessian of the function. So first, you can observe that the Hessian of log of g is exactly this quantity. So what is this quantity? It is g times the Hessian of g minus the gradient transpose over g squared. Okay. Now, here I'm going to deal with functions that have non-negative coefficients. Okay, and I'm going to only look at log concavity over these functions. So I'm assuming that g has non-negative coefficients. X is non-negative. So this says that the evaluation of g at x is non-negative, and so is g squared. And so g is so g is non-negative, and therefore this inequality essentially tells me that that the Hessian is at most gradient transpose up to some normalization. Okay. Now, this matrix, the gradient transpose, is a rank 1 matrix. So this tells me that the Hessian has at most one positive eigenvalue. Okay. So you can see that the converse is also true if you have a homogeneous polynomial, but I'm not going to tell you that. I'm going to talk about that. But basically, that's the point. That so in other words, whenever I say I have a log-concave polynomial, you can assume that the Hessian of the log is negative semi-definite, or the Hessian has at most one positive eigenvalue. So let me tell you one immediate consequence of this. So here is an immediate consequence that for any matroid, you don't get negative correlation, but you get approximate negative correlation in the following sense. The negative correlation between like any pair of elements I and j is like, if you had negative correlation, these two would have been 1. Probability of I and j would be at most probability of I times probability of j. But now that you have approximate negative correlation, this 1 is going to be 2. And more generally, if you look at a random pair of elements, you get approximate negative correlation of, say, n over n minus 1. So it's like very close to 1. So this, it gives you an indication that maybe this log concavity is useful. And that was the starting point of our project. So we said that, okay, from this strong log concavity, we get approximate negative correlation. We know negative correlation is useful. So maybe we can prove that approximate negative correlation is also useful. But let me not, I mean, I include the proof of this theorem here. I'm not going to go over it. It's a simple exercise. But basically, the question we had was that, okay, now that we have approximate negative correlation, maybe we can say that fractional matchings exist again. But we tried a lot. The best we could prove was to lose the exponential loss in the number of elements. So we couldn't prove that good fractional matchings exist. And it seems that the canonical path method is dead. Okay. So, but at least we have a tool. And I want to tell you how to use this tool. Okay. So let me tell you now. I want to tell you now about random walk. So this would be hopefully quick. Hopefully many of you are familiar with random walks. At the end of this section, I'll tell you one application of this strong log concavity somehow related to random walks. Okay, and then we'll see a bigger picture of what is going on. Okay, so let me very quickly tell you about random walks. Okay, let's say you have a graph, you have a weighted graph, you can study random walks on it. The simple random walk is that when you are at vertex 1, you choose an edge incident to 1 proportional to its weight. So you choose 3 with probability 1/2 here, and you move the corresponding neighbor. The stationary distribution of such a walk is that the probability of every vertex is proportional to its weighted degree. And we know that if the graph is connected and non-bipartite, the random walk will mixes to the stationary distribution. So these are known facts. If the graph is bipartite, it's still not a big deal. You can add loops to the node, so-called make the walk lazy, and still you will converge to the stationary distribution. So this is known facts about random walks. There is this other thing called mixing time, which is basically a metric on how close are we to the stationary distribution. So the mixing time is t of with respect to epsilon is a time t that no matter where you start the walk, if you start the walk at any vertex I of your graph, at time t, your distance, say L1 distance with respect to the stationary distribution, is at most epsilon. So that's called the mixing time. It's a minimum t that this happens. So let's say at time 100, my distance is at most 1/100 from the, or some epsilon from the stationary distribution. And this is a classical fundamental theorem for studying mixing time. If you have a graph, if you know the eigenvalues of the graph, the mixing time is at most such a quantity. So at most a log of 1/epsilon pi star. Pi star is the minimum of like minimum probability, minimum of the probability of all starting states, and or minimum probability of all states at the stationary distribution. And here we have max of the second eigenvalue and absolute value of the smallest eigenvalue. Okay. Again, here the lambda n is not so much of a big deal. We can add loops and forget about lambda n. So essentially, the main thing is 1 minus lambda 2, which is the spectral gap. Okay. So here is the picture I want you to keep in mind. If you have a random walk, if lambda 2 second eigenvalue of the transition probability P matrix of the random walk is small, let's say less than 1/2, then the random walk mixes rapidly. Okay, so these graphs satisfying this are called expanded graphs. They mix very rapid. The mixing time log n. Basically, we typically think of epsilon as a constant. So if pi star, if the stationary distribution say is uniform, your graph is regular, the stationary distribution is uniform. So pi star would be 1 over the number of vertices of your graph, and here you would get some constant times log of the number of vertices. That would be your mixing time of your Markov chain. Okay. So this log is really small because we're paying. I mean, even though so the nice thing is that even if we have exponentially many vertices, many states in our Markov chain, because we're paying log here, this doesn't matter so much. So that would be the case for our for a random walk we're going to run on the basis of the graph, on the basis of the matroid. But this quantity, the spectral gap, is really the main issue. So the spectral gap in general can be inverse polynomial in the number of vertices, number of states of the Markov chain. So if you want to get mixing time, which is logarithmic in the number of states, we need to say that the spectral gap is small. It's like either constant or logarithmic in the number of states. Okay, cool. So that's about mixing time. Now, before telling you the actual Markov chain that we're going to run, I want to tell you one application of using strong log concavity to study random walks. Okay, on matroids. So here is a simple application. Let's say I have a matroid. G is the generating polynomial of the matroid. I construct a graph on the elements. So this is a different graph. This is not a graph on all the bases of my matroid. This is a graph on elements of my matroid. And the weight of an edge connecting two elements is exactly going to be the number of bases that have these two elements. Okay? Which is exactly the Hessian of the generating polynomial at ij. Okay? So it's exactly the number of bases that have I and j. Now, I consider a simple random walk on the graph G. So here is a simple example to keep in mind. Okay, so if this is the matroid, this is exactly the Hessian matrix, and you get such a, so like here 2 is a number of bases that have elements 1 and 2, and you can see here that there are 2 bases that have z1 and z2. Okay, so you get such a graph. Now I told you that the Hessian matrix has at most 1 positive eigenvalue. In fact, exactly 1 positive eigenvalue. So what you get is the second eigenvalue is less than or equal to 0, and therefore the spectral gap of such a Markov chain is at least 1. So it mixes very, very rapidly. Okay, so what am I saying? I'm saying that the strong log concavity tells you that some Markov chain, some random walk on the elements of your matroid mixes very, very rapidly. This is not the random walk I really want. I really want to run a random walk on basis. Here I'm running on the element, but as we will see, it is very closely related to the random walk I want to run on the basis of my Markov chain. Any questions here?
The fact that the entries are positive, is that from the definition of G?
Yes, the entries are positive. Yeah, I'm assuming that G is a strong log concave with non-negative coefficients. So entries are exactly the number of bases that have elements I and j. Any other question? Okay, so if not, let me tell you how we study the Markov chains on bases. So we use this a very beautiful area of high-dimensional simplicial complexes, and it turns out that you can see matroids as special cases of simplicial complexes, and you can use machineries there to study this. Okay, so basically, like roughly speaking, what we use is that we use this machinery of a strong log-concavity with a machinery of high-dimensional simplicial complexes to study Markov chains on random walks. Okay, so because of that, I again have to tell you about the new tool, high-dimensional simplicial complexes. So what's a simplicial complex? It's just a downward closed family of subsets. Okay. So in particular, like for example, you can look at set of cliques in a graph. That's a downward closed set. So it is a simplicial complex. Another example is the independent sets in matroids. So we said that independent sets are downward closed. So that also defines a simplicial complex. So this field has its own terminology. So we call face a subset in the simplicial complex X. Let's say the dimension of a face is the number of elements in that set. Typically, I define it to be number of elements -1, but it's nicer for our application to define it to be the number of elements. Dimension of the simplicial complex is the maximum dimension over all of the sets, exactly maximal size. And I'm going to use this notation x of k to denote all faces or independent sets when you deal with matroids of size k. And here is an important definition. We say simplicial complex is pure if all maximal faces have the same size. So remember, we said that for matroids, all maximal faces have the same size because of the exchange property. So this says that matroids are pure simplicial complexes. So here are two examples. Here I have faces of dimension 1, which are the vertices, dimension 2 are the edges, and dimension 3 are the triangles. The left simplicial complex is not pure, because if you look at 2, 3, that's a maximal face, but it has size 2, whereas 1, 2, 3 is a maximal phase of size 3. Whereas the right one, I also have the green triangle, is a pure simplicial complex. So again, just to fix the terminology, this is how matroids and simplicial complexes are related. Independent sets are exactly faces in simplicial complexes. Pure simplicial complexes, matroids are pure simplicial complexes because of exchange property. The rank in matroids are exactly dimension in the simplicial complexes. Okay. Now that we know simplicial complexes, we can use the machineries there. So okay, so I already told you that if you have expanded graph, a graph where second eigenvalue is small, the random walks meet rapidly. Now, recently there has been a lot of works studying analog of expanded graphs for high-dimensional simplicial complexes. And basically, here is the way it goes. It says that if you have a simplicial complex, you can study like analog of adjacency matrix, Laplacian matrix, random walk matrix, and so on. And basically, there is this notion called localized random walks or localized Laplacians or localized adjacency matrix. If these objects have like large spectral gap, then you have so-called the high-dimensional expander. Okay, so this method is a local to global method, which allows you to go from like local Laplacians to like global Laplacians or global random walks. And then recently there has been more works which say essentially that when you have a high dimensional expander, you can study random walks on it and they mix very rapidly. Okay. There have been a lot of applications in this, property testing or let me say. Okay, so let me tell you what we do. We basically say that when you have a strong log-concavity, it implies that these localized Laplacians have large spectral gap. Okay, so I already told you that when you have a strong log-concavity, some matrix on elements of the matroid have larger spectral gap. Okay, that matrix I defined like 2 slides ago, that is exactly the localized Laplacian or localized random walk matrix. I'm going to define it formally, but that's exactly the matrix. Okay, and I exactly told you that a strong log-concavity implies that. So that's sort of the crucial observation. So it basically allows you to go from here to there, and essentially the rest of it is has been done. Okay, so let me tell you. Okay, let me tell you about what all of these terminologies mean. What is a high-dimensional walk? What's a high-dimensional? What's a localized Laplacian, and so on. So first of all, what's a high-dimensional walk? So this is defined by Kaufman and Oppenheim, and it was a follow-up to several other works, Kaufman and Maas, and Kaufman and Dinor and Kaufman. So you say that, let's say you have a simplicial complex X of dimension R. Feel free to assume that it is just independent sets of a matroid. You can construct a bipartite graph G of R as follows. The vertices, like on one side, you're going to have like independent sets or bases of size R. On the other side, you want to have near bases or faces of dimension R minus 1, independent sets of R minus 1 elements. You're going to have an edge if an independent, like if the bottom vertex is a subset of a top vertex. So here 1, 2, 4 is a base, 1, 2 is a subset of that. So I'm going to have an edge. I'm going to run a random walk on this graph G of R. Okay, so how do I do it? Just as you expect. I start from some vertex. I look at all of the neighbors, choose one of them uniformly at random. I look at all of the neighbors again, choose one of them uniformly at random, and so on. Look at the neighbors, choose one of them uniformly at random. Look at the neighbors, choose one of them uniformly at random. Okay, so as you see, I'm running this walk on the bipartite graph. This induces a walk on the basis itself, right? I can just look at the top part of, I can just look at the top portion of this I think my video is stopped. Something happened. I can just look at the top portion of this Markov chain just on the oops. Just on the basis, and I define that to be P of R. So I'm going to use this notation down up. So see here, down up. P of R down up means that you start from R, you go down, and then you come up. Okay. Good. So one thing you can observe is that the degree of every vertex in the top is R. Why? Because every vertex in the top has R elements, and every subset of it, it's downward closed, right? So every subset of it of size R minus 1 is a vertex below. So I exactly get R subsets below that have edge to it. So the degree at the top is R. So the stationary distribution at the top is uniform. This is not true in the bottom. In the bottom, the degree is not necessarily the same. So in fact, the degree of every vertex in the bottom is exactly the number of bases that have that element. Okay, but I'm interested in the top. So in the top, I have uniform, and this, you can see this this graph is connected using the exchange property of the matroid. So you can hope that this Markov chain gives you a random base, and that's exactly what we prove. That if you run this Markov chain on any matroid, it mixes rapidly. And in fact, you can think about it, and you see that this is just a weighting on the basis exchange graph. So in fact, I'm just running the chain on the basis of a matroid, and two bases are connected if they differ in exactly like if the symmetric difference is 2. I just have a weighting of the basis exchange graph, and I show that it works. Okay, so here is basically what we show. If you look at eigenvalues of this PR down up, this is a PST matrix. Its second eigenvalue is at most 1 minus 1 over R. So the spectral gap, which is the difference of 1 and the second eigenvalue, is exactly 1 over R. Okay, so from that, we get that the Markov chain mixes in time R times log of the number of bases. In any matroid, you have at most n choose R many bases. So this gives you a mixing time of R times log of n choose R, which is essentially R squared log n. Okay, we can also study other eigenvalues of this chain. You get such a thing. basically the thing is, if you look at the hypercube, second eigenvalue is exactly 1 minus 1 over log of the dimension, and we exactly get that. And this pattern also matches the pattern of eigenvalues that you see for the hypercube. So in a strong sense, hypercube is a tight example for this theorem.
For mixing, you don't actually need all the eigenvalues, right?
Yes, for mixing, you just need the second eigenvalue. The rest of the eigenvalue can actually help you to improve the mixing. So that's something we haven't managed to do yet. So this log of n choose r can potentially be improved when you know other eigenvalues of the. So in hypercube, you actually pay log of the number of variables. So there's another log here, which improves the running time, which is gonna, like, the mixing time in the hypercube, like this r squared is really r. And we cannot do that yet. Basically, the fact that we can study other eigenvalues allows us to say that if you start from a random starting point, the mixing time is good. We cannot study the worst case starting point yet. Any other question?
Maybe this is for later, but I'm kind of wondering how much do you need of the machinery of high-dimensional expanders? Because basically, it looks like just a graph. It's not a hypergraph, right?
Yes. And in fact, we're going to study it just considering that it's a graph. I mean, okay, what do you mean? I mean, the thing is, we can rederive all of their proofs. So I'm gonna tell you how to prove this, or give you some ideas at least. The thing is, we can rederive everything, almost everything they've done, just in a graph language without using their language.
You can do this yourself.
Yeah, that's something we did, to rederive everything in a sort of more like a spectral graph theory like language. Okay, so let me tell you like how to think about it. So first, okay. So first, let me first do some simple observations. So let's say this is the graph I want to talk about. Let's say you have this PR, which is this is the transition probability matrix of the bipartite graph. Okay. So if you look at it, there are oh, sorry, there should have been a 0 here. So there are like because this is a bipartite graph, there are two submatrices. PR minus 1 up says that if I start from a vertex in the bottom, I do one step, I go up. And PR down says that I start from a vertex in the top, I do one step, I go down. Okay, so this is the transition probability matrix of the bipartite graph. Now, if I look at PR squared, this is like taking 2 steps of the walk in this bipartite graph. So, sorry, it's another. Okay, sorry, this should have. These two should be on the diagonal, in the left. This should move to the left. This should move to the right. So, so how do you do 2 steps of the walk? Either you start from the top, you go 1 step down, then you go 1 step up, or you start from the bottom, you go 1 step up, then you go 1 step down. Okay, so the matrix PR squared is exactly this matrix. The upper left corner is PR of down up. The bottom right corner is exactly PR minus 1 up down. Okay. Now, the important observation is that I have a PR. If I look at PR squared, it's a PSD matrix. The eigenvalues of this matrix is exactly square of the eigenvalues of that matrix. So PR squared has non-negative eigenvalues, which in particular implies that these two, these two blocks, because it's a block diagonal matrix, these two blocks are also PSD. The second fact you get is that because PR down up is just PR down times PR minus 1 up, and the other one is the opposite. These two matrices have exactly the same eigenvalues, because AB, like for any two matrices A and B, AB and BA have the same eigenvalues. So PR down up and PR minus 1 up down have exactly the same eigenvalues. And in particular, lambda 2 of PR down up is the same as lambda 2 of PR minus 1 up down. So instead of studying lambda 2 of PR down up, I can study PR minus lambda 2 of PR minus 1 up down and say that's at post 1 minus 1 over R. Now this starts to seem like an induction, and that's exactly what we're going to do.
So one of the matrices is bigger. They're not the same size, so they cannot have the same eigenvalue.
PR down up is bigger. Yes. So in fact, PR down up has more zero eigenvalues, but the non-zero eigenvalues are exactly the same. PR down up could be bigger because you have, let's say, more bases than near bases, than independent sets of size R-1. Okay, so now let me tell you the induction. How does the induction go? So you can complement this graph. So far, I was studying the top two part. You can complement it, go all the way down to the empty. And you can study the eigenvalues of PR-1 up down inductively. Okay. First, we need to figure out one thing. We said that the stationary distribution in the top is uniform. If you look at the stationary distribution here, the probability of a vertex, I said, is exactly the number of bases that contain this vertex. So if I want to study these eigenvalues inductively, I want to study a random walk matrix in the next level, which gives me the same stationary distribution. So basically, we need to define a notation. Let's say W of a vertex is exactly summation of W of everything above it. So W here, let's say W at the top, the weight at the top is 1. Like the weight of this guy is 2 because it's 1 plus 1. The weight of this guy is 4 because it's 1 plus 1 plus 2. So the weight of everybody is exactly the summation of weights of nodes above. Then you can actually see that up to a normalization, the weight of every node is exactly the number of bases that have that node. Okay, so this exactly gives me that this exactly will be the stationary distribution at every level of this inductive Markov chain that I'm going to study. Okay, so first I'm going to weight every edge by the weight of the node above it. So in the first level, the weight of everything above was 1, so the weight of these guys will be 1 at the first level, at the top level. But the next level, like this weight is 2, so the weight of this edge would be 2. Now I just run a simple random walk on the weighted graph I get from the weight of the edges. You can analogously define PK to be the random walk on, say, independent sets of at level k and k minus 1. You can look at lambda 2 of. You can say lambda 2 of pk down up is the same as lambda 2 of pk minus 1 up down. Everything like that works. And the main lemma that we prove is that pk up down is at most pk down is at most an averaging of pk down up and the identity, where you scale this one by k over k plus 1 and this one by 1 over k plus 1. Okay, so this is the main lemma. Let me tell you, if this is the main thing, if you have this, you'll be done. Because okay, so basically you have these two facts. Lambda 2 pk of down up is lambda 2 pk minus 1 of up down, and pk up down is at most such a thing. Now you can use induction. You can say that, okay, p1 up down is at most 1/2. That's not hard to see. It's just the base of the induction. Now so you have p1. So then from this I go to p1 of down up. Then wait a second. No, sorry. From this I go to p2 of down up. Then I use this one to go to p2 of up down, and so on and so forth. So basically you just plug these two inequalities in for all k. You get that lambda 2 of p1 was 1/2, 2/3, k over k plus 1. And in particular, lambda 2 of PR is at most 1 minus 1 over r. Okay, so it all boils down to proving this inequality, this PSD inequality. Any questions? Okay, so if not, let me tell you the last part, how to study such a thing. So the idea is to, I haven't told you what are local Laplacians or local random walks, but the idea is to use that to prove this inequality. So I'm going to define a local spectral expander. Before that, let me tell you some how to think about random walks locally. So let's say you have a simplicial complex X. You look at the face of that complex, and you define so-called the link. The link of a face is basically all faces or all independent sets that contain that independent sets where you remove this part. So here, let's say this is a simplicial complex. I look at all faces that contain 4. I remove 4 from them. So like 1, 4, I remove 4, I get 1. 2, 4, I remove 4, I get 2. And then 1, 2, 4, I remove 4, I get 1 and 2. And similarly here. Okay, so this is called the link. In matroids, this operation is called contraction. That's exactly contraction. So just for another example, this is a graph. This is the weighted graph I was talking about. If you look at, again, some vertex 2 here, the link is exactly all of the nodes above it, all of the bases and independent sets that contain this guy. I remove everything else, and then I remove 2 from them. This is called the link. It's another simplicial complex, but only on subsets that contain a particular independence or a particular face of a simplicial complex. Okay. One more definition. You can study one skeleton of a link. So what's one skeleton of a link? It's a graph on level 1 and level 2 faces above a link. So here I can construct a graph with 3 vertices, 1, 3, and 4, and each of these, the next level, give me an edge. I'm going to get an edge from 1 to 4 with weight 1. I'm going to get an edge from 3 to 4 with weight 1 as well. Okay, so you can do this in general. Let me do an example for the partition matroid. So let's say you have a partition matroid. Remember here, you have like 2 to the n many bases where you choose one element from each bucket. So let's say I fix 1. I want to look at the link of 1. I want to look at one skeleton of the link of 1. So every element besides 1 in blue actually gives me an independent set. Like 1 and 2, for example, give me an independent set. 1 and n give me an independent set. I have an edge between 2 and n because there are many bases that contain 1, 2, and n. Okay. I don't have an edge between 2 blue and 2 red because there are no bases that contain 1, 2 blue, and 2 red. Okay. So you get such a graph. This graph is exactly a complete multipartite graph, and every edge in this graph have exactly the same weight. It's like there's a normalizing factor. It's like 2 to the n minus 2, which is like the number of bases that contain 2 and n. Okay, so this is one skeleton of the link of element 1 in a matroid. You get in a partition matroid. You get this way. Okay. Now, having this in mind, I can tell you what is a local spectral expander. We say a simplicial complex is a local spectral expander if the simple random walk you consider on the one skeleton of a link has very good eigenvalues. So let's say this p tilde 1 tau means that I look at the random walk on the one skeleton of x of tau. It's just a simple random walk, non-lazy, just and on the one skeleton of x of tau, we say x is a lambda local spectral expander if the second eigenvalue of p tilde 1 tau is at most lambda for every tau. Okay, so again, here is an example. You look at the hypercube, you look at 1. This was the one skeleton of 1. I want to look at the simple random walk on this graph. I want to look at the second eigenvalue of the simple random walk on this graph. Okay, and it's a fact that if you have a complete multipartite graph, the second eigenvalue is equal to 0. Is less than or equal to 0. In fact, in this case, it's going to be equal to 0. So for any complete multipartite graph, the second eigenvalue is at most 0. So you get that a simplicial complex on the partition matroid is a 0 local spectral expander. Now the fact we prove is that this was not a coincidence. This is true for every matroid. That the simplicial complex is 0 local spectral expander, meaning that the one skeleton, the random walk on the one skeleton of the link of every face has second eigenvalue at most 0. And the proof is exactly again the thing I showed you before, that it follows just from strong log concavity. Okay, so let me. Okay, can I have like 4 more minutes, or should I finish?
Yeah, go ahead.
Okay, so just to show you the overview, basically, okay, so basically this was what we wanted to prove, and that would tell you that the second eigenvalue is good. What we show is that when you have a strong log concavity, that implies that your matroid is a zero local spectral expander, meaning that the second eigenvalue of the simple random walk on the one skeleton of the link is at most 0. There is this other fact, this follows from Kaufman-Oppenheim, that you can, so see this inequality I want to prove. Move the things in the right-hand side to the left, you get this object. Okay, this is exactly this right thing moved to the left side. So this is the object. They prove an identity, that this thing exactly equal to summation of the one skeleton, the summation of the random walks on the one skeleton of the links at level k-1. There is just one simple thing. This notation means that I take off the part parallel to the all ones vector. So I look at the random walk matrix modulo the top eigenvector. Okay, so that top eigenvector gives me eigenvalue of 1. When you take it off, this matrix is negative semi-definite. So this sum is also a negative semi-definite matrix, which proves this. So this identity, this is an identity. Okay, so it's, you need to write some lines of arguments, but it's just an identity. So it's not like, in some sense it shouldn't be so hard to prove. And once you put these two together, you get a local to global reduction. When local random walks are good, global random walks are good as well. So this sort of method is called the Garland method, which allows you to say, whenever local random walks, like random walks on one skeleton of links, are good, then the global walk on all of the simplicial complexes are good. The Garland method was originally used for Laplacians, to say that when local Laplacians are have good eigenvalues, whatever that means, have large spectral gap, then the global Laplacian also has good eigenvalues. But the important thing is that here you need very good. If I substitute this 0 with 1 over the dimension of the simplicial complex, this local to global thing still works, and I still get a Markov chain which mixes rapidly. But if this is 1/2, although for random walks on graphs this was good, this is no longer good. The method doesn't work anymore. So you need the local random walk to be very, very good. To be the second eigenvalue, you need to be very, very close to 0. Even like an expander-ish good, like 1/2 is not good enough to get a mixing of the global walk. Okay, so okay, so I wanted to tell you one line about proof of this, but I think I'm going out of time. Let me sorry. Okay, so let me skip this. Basically the point is that okay, let me say one sentence. The point is this. The point is that the adjacency matrix of the one skeleton of a link is exactly the Hessian matrix of the of a derivative of the generating polynomial of a matroid. Okay. Now I told you that if a matroid so I told you that for every matroid, the generating polynomial is a strongly log-concave, meaning that if you take partial derivatives, it remains log-concave. So that says that the Hessian of this has at most one positive eigenvalue. This tells you that the adjacency matrix of the one skeleton of a link has one positive eigenvalue. Therefore, the random walk matrix has one positive eigenvalue, and the second eigenvalue is non-positive. So that's pretty much it.
Very, very dense. What does it look like? It has such a low eigenvalue. It means it's almost.
Yes, it means that it must be a complete multipartite graph. So this is a simple fact to see that if you have an unweighted graph, the second eigenvalue is at most 0, if and only if it's a complete multipartite graph. But here, the graph that we have is not unweighted; it's weighted. So that's not such a simple fact. Okay, but it's true. Okay, okay. So anyway, so the point is this method I told you about matroid is more general. You can, in general, you can prove, you can sort of relate the language on simplicial complexes to the language on polynomials. Like if you have a simplicial complex with some arbitrary weighting on the top faces, like pure simplicial complex, you can construct a polynomial that way, and then you can relate many of the terminology in simplicial complexes to polynomial. Dimension will be the degree. Pure means that your polynomial is homogeneous. When you look at the weight of the empty set, it's like evaluating the polynomials. The links correspond to taking derivatives, like partial derivatives. The adjacency of one skeleton is exactly the Hessian of the partial derivative of G. Localized random walks correspond to some normalization of the Hessian. So you can study polynomials using simplicial complexes or simplicial complexes using polynomials. That's basically what we have been doing and we are doing right now to basically relate these two fields. So you get this as a consequence. You get many other consequences. You basically get that not only for matroids, but for any strongly log-concave polynomials, as long as you have access to the coefficients, you have Oracle access to the coefficients, you can evaluate the polynomial at any point with non-negative values. Okay, so you get such a thing as well. This itself has many other applications. You can, if you're familiar with a Toth polynomial, you can compute the random cluster model or a Toth polynomial in some regime where Q is between 0 and 1. It's probably the first non-trivial regime that you can approximate the Toth polynomial. You can study so-called smoothing of determinant point processes. Let me not tell you about that. Yeah, basically, like at a very high level, what we're doing is that we're relating these three fields. I haven't told you what Hodge theory is, but that was something we originally used to prove to prove that generating polynomials of matroids are log-concave. Now we use log-concavity related to high-dimensional expander. There are also some connections between high-dimensional expanders and Hodge theory. So yeah, there's many things going on about like better understanding the connection between these fields. Okay, so I'm out of time. I just stopped with this slide. So there are many interesting questions. Can we use this machinery for other like sampling problems going beyond matroids? Can we improve the running time, the mixing time from R² to R? And the other thing is that this Mihail-Vazirani conjecture was proposed for any convex hull of 0, 1 vectors. We proved it for matroids. It's open for other 0, 1 polytopes. So although I'm not sure if there would be like other like computational application if we prove it for other 0, 1 polytopes. Okay, let me stop here. Let me know if
you Chad.
Yeah.
And we'll see everyone in 2 weeks. Let me take us off.